in vectors, there's two kinds of multiplication. We learned the dot product or the scalar product. And sometimes it's nice to call it the scalar product because the answer is just a number, and the word scalar means just a number. The cross product, the answer is another vector. So we're going to find a cross product, and that vector that the answer is will be perpendicular to the two vectors that you started with. Now the cross product works in both 2 dimensions and 3 dimensions. Anytime you would draw, like technically, these two vectors could be in 3 dimensions. I just drew them in class, right? But they happen to be perfectly on the smartboard. Any 2 vectors that you draw anywhere in 3 dimensions, there will always be a flat piece of paper that you could place them on, somewhere. It might be bent or diagonal or something like that. We call that flat piece of extended paper for everywhere a plane. So a plane in a 3-dimensional space is just a 2-dimensional flat piece of paper that extends forever. So no matter where your 2 vectors are, there will always be some place that you could put that flat piece of paper, and you could always draw something straight out from there that would be perpendicular. And you could do that in 2 directions. It could either come straight out this way, or it could go inwards. So here is the formula for the cross product. Our first formula for the cross product. We'll find 2 different ways of figuring out the cross product. You take the length of the one vector times by the length of the other vector times by sine of theta. All of these will be numbers, and then that gets multiplied by a unit vector in a certain direction. Like I said, it could be perpendicular sticking out or perpendicular sticking in, and we're going to find out that the way that we can figure out which direction it goes follows something called the right-hand rule. Some of you might have learned about the right-hand rule in physics and stuff like that. It's going to be very similar to that. I'm actually going to give you, some people can't use the right hand very well. I don't know. I'm not sure if this is like, does the right-hand rule have historical reasons against left-handed people? No. It's just what works. Okay? So we're going to figure out another way to also explain that. But this is how the right-hand rule works. When you draw 2 vectors, and I've got a picture, I think. Let me double check your notes here. They go. Yes. I've got pictures for you as well. Well, they're a little bit dark, but what's going to happen is you're going to draw your 2 vectors, u and v. Here is the picture. You have 2 vectors, u and v, and you start by putting your hand on the first vector. So here's your hand completely flat. You would put that on your vector u in a way so that you could bend your bottom 3 fingers. I can only bend them this way. In this situation, when I bend it towards V, sometimes I like to draw an arrow there that your fingers are bending towards that way. Then my thumb is pointing out towards me or upwards out of the paper. If I had started on V and done V cross U, I can't put my hand here and bend my fingers backwards. It hurts. You can try, but it doesn't work very well. So I have to put my hand on this way so I can bend my fingers backwards. And in this case, my thumb would be pointing inwards into the paper. So the right-hand rule is a way to determine whether it's going to be inwards or outwards. And I find it somewhat, like, see students sometimes on a test going, they just start staring at their hand and they don't know how to move it and they're very confused. So I have found another way of explaining this that I think is more intuitive, okay? If, and this is based on an assumption that you guys brush your teeth, okay? If you don't brush your teeth and have never seen a tube of toothpaste before in your life, you're going to have to go with your right hand to figure this out. Okay? But if you had a tube of toothpaste and you went U cross V, meaning starting at, whenever we do U cross V, we're starting there, and then the arrow is going towards V. Imagine holding toothpaste right here and turning the toothpaste knob. Will it loosen or will it tighten? You've done it often enough. You don't even think about it. But great, just now you're going to be on a test pretending to hold toothpaste and twisting it. If you want to loosen it, do you see that this way would loosen it? If it loosened, which way is the cap coming? It's coming off, out of the paper. If you tightened it, which way is the cap going? It's going on tighter into the paper. I find that a much easier way to envision it. In fact, one of the applications we're going to do is the same thing with torque. If you put a wrench on a nut on vector U and turned it towards vector V, it would loosen it. Now, we're assuming that things are threaded the normal way. There are some things that have reverse threads. Never have I ever got a, it'd be like, you want to mess with people? Design toothpaste with reverse thread. They'd be like, I can't get my toothpaste open. Terribly, it'd be funny to watch. Like, watch a person get the toothpaste that has reverse thread. They'll be so confused. Okay? So we're used to the majority of things, when you turn it this way, right, you'll loosen it. If you have never brushed your teeth, maybe you've opened a bottle of Coke or Pepsi. It's like, yeah, I have no experience with toothpaste, but I do know how to open a pop can, or not a can, open a pop bottle. Same thing, right? Turning it this way would loosen the cap. Turning it this way would tighten it. So for all those people out here that don't brush their teeth, there is another option for you. Just make sure you bring a bottle of Coke to your exam. That'd be hilarious. It'd be hilarious if someone would get close to her exam. Someone says, can I bring some toothpaste? If you need to bring a thing of toothpaste to the exam, feel free. Okay. So here, this is all of the stuff in words that I was just saying, right? We can also think about a wrench, tightening a bolt, or loosening the cap of your toothpaste, which direction it would go. So this means that the cross product of U cross V and V cross U are not the same, mainly because the direction will be different. The numbers would be the same. The only difference is that one would be coming out of the paper and one would be going into the paper. So they're just in opposite directions. So what we can say is we can say U cross V is the same as negative V cross U. Because it'll be exactly the same length, just in the opposite direction. So here we have two vectors. We want to find U cross V, which I'll do in blue. If you have U cross V, this is the direction that you would be thinking of, or that is how you would set up your right-hand rule, pointing this way and moving your three fingers towards V. And V cross U, in green, that would be in this direction. So if we start with the blue one, U cross V, it's going to be the length of U times the length of V. Times sine theta times n in the direction upwards. We know that the length of U is 10, the length of V was 20, the angle in between them was 50 degrees. then we can type all of this into our calculator. Make sure your calculator's in degrees. Then we get 153.2 . And we have to define which way n is going. So just writing n doesn't tell us which direction it's going. We have to figure if I'm going u cross v, right? My right-hand rule, I can go like this. I can see that it's pointing outwards. If you think about taking a cap and turning it in that blue direction, it would loosen. And if it's loosening, it's coming out. So we have some way of saying this idea that it's coming outwards. Two different ways that you could then do v cross u. The easiest way to do v cross u is that it's exactly the same but going inwards. So we could just take the answer that we had and put a negative in front. Since we've already defined that the unit vector n was outwards, by putting a negative there, that makes it go inwards. Or the other thing you could do is you could choose another letter and make a unit vector w, and then write out the unit vector w points inwards and write a statement. But mathematicians don't like writing stuff. I feel like there should be some sort of, like, why couldn't we do n and then have a little arrow, and the arrow's up, it means outwards, the arrow's down, it means, you know, we could create some sort of new, who knows, maybe there is a really good notation out there that would allow us not to write more words, but I don't know. So we've got a cross product, it figures out some number, and it points inwards or outwards. Now, when we figure out some number, we're sort of like, well, what does that number mean? Why would I want to do this? We're going to get and find out some applications of this as well. The first application is that the cross product can help you find the area of a parallelogram. And I'll show you how. Here we have a diagram of a parallelogram that's made using two vectors. In other words, if I take a vector u here and a vector v here, and I clone them, I can move this one and attach it up there, and this one attaches perfectly from there to there. It makes a parallelogram perfectly with two vectors, because you can just copy those vectors over and over again. Now, your formula for the area of a parallelogram is just the base times the height. And the reason it's just base times height is because if I took this triangle over here, cut it off, and moved it over here, I would make a perfect rectangle. And you know the area of a rectangle, just length times width, or base times height in this situation. So it's a really nice visual saying, oh, I just cut this piece off, moved it over here, now I make a perfect rectangle. So that visual should help you remember the area of a parallelogram forever. Now, how do I do that? Well, I just need, right, the area is going to be the base, which is the length of u, times by the height. There's my area of my parallelogram. Now the height, if I introduce an angle theta right here, The height and the green line, my hypotenuse, are part of that triangle. I could write out by definition of sine that sine of theta is opposite, which is the height, over the hypotenuse, which happens to be the length of my vector v. If I rearrange this, I can get the height by itself is just the length of vector v times sine of theta. And then if I substitute that into my formula here, this is just the magnitude of the cross product. Because the only thing missing here from the cross product is that unit vector that would be at the end. There's our formula for a cross product, happens to be the magnitude of our cross product happens to be exactly the same as what you would get if you wanted to find the area of a parallelogram. So you now can figure out the area of any two vectors that are connected to each other. So in the question that we just did, we got an answer that U cross V was 153.2 pointing outwards as a unit vector. So the area, the magnitude of this will be 153.2. Now there's no units given in here. Units squared. But if there were units, we could add those units as well. Now you could have found that area using your regular math as well, but we're going to find that as soon as you move into 3 dimensions, your regular math doesn't work very well. And now the cross product, you could find the area of a parallelogram in 3 dimensions formed by 2 vectors quite easily as well. Which gets us to the Cartesian form of the cross product, a second formula. And just like the dot product, where things could be calculated quite simply to help us find cos of theta, one of the problems with the initial formula of the cross product is you needed the angle theta and you needed sine of theta. Well, the Cartesian form gets rid of the theta. Okay? Now, the formula, upon looking at it first, makes you feel like, oh great, there's just a bunch of letters and numbers randomly put there. This is going to be hard to memorize. Yes, if you just try to memorize it directly, it will be hard. However, we can use something we learned in matrices to help us remember this formula. This formula is very similar to determinants in matrices. In fact, it's very similar to something we did with the determinant for a 3x3 matrix in some ways. So, in order to find what's going to go in row 1, we go to our initial ones and cancel out row 1, and then do the determinant. Remember we did the determinant like this, where you multiplied these and subtracted? Notice A2 times B3, that's there, and B2 times A3 gets subtracted there. For the second one, we would now cancel out the second row. And same thing, we think of our determinant, but I don't know if you remember in our 3 by 3 determinant, in our 3 by 3 determinant, the first one was plus. When you canceled out the second one, it was negative, and the third one was plus again. You probably don't remember that because you probably like the arrow way of the 3 by 3 determinant better than the formula way. And that's perfectly fine. I'm going to show you an arrow way with this one, which you can like better, and not have to worry about this as well. Okay? But what it's going to be is, in this second one, if I did my determinant, it would be A1, B3 minus B1, A3. And if that negative got distributed, can you see that now the B1, A3 would be positive, and the A1, B3 would be negative? So it does alternate plus, minus, plus. And the same thing to find row 3, you would ignore row 3 and do your determinant with what is left. So similar to what we did just when we had a 3 by 3 matrix, to find the determinant, you took this number, ignored everything else, and multiplied it by the determinant of what was left there. Then you took your second number, ignored everything else, and multiplied by the determinant of what was left, but with the second number you added a negative. Same thing that we're adding a negative here. And then the third one, you'd ignore everything else and do the determinant for what's left. That was one method of finding our determinant of a 3 by 3, but you guys afterwards much preferred this technique, right? For determining your determinant of your 3 by 3. So we're going to find out a similar technique for doing the cross product algebraically with vectors. Okay? The way that it works is you will write out the unit vectors ijk twice. Then you will take your first vector u and list it under I, j, and k twice, and then your second vector v and list it under I, j, and k twice as well. So this is what it's going to look like with an actual example. And we'll do this actual example using both formulas and both ways. So we want to find u cross v. First of all, we'll use the first technique. In the first technique, you would ignore the first row and then do the determinant of what is left. So I would get negative 8 minus 15. This would give me my negative 8. This would give me 15, but then I'd have to subtract. For my second one, I would ignore the second row. I'd put a negative and brackets out in front. And then I would do my determinant would be 16 minus negative 30. And finally, I would ignore my last row and do the determinant 6 minus 6. So this simplifies to be negative 23, negative 46, and 0. method 2.
Shouldn't it be 14? Because it's minus 16 minus plus 13.
Okay, so I did inside the brackets first.
Okay.
So 16 plus 30 would be 46.
Yes.
Times by the negative.
Oh, you're right. Sorry.
Yeah. No, it's good. So I'm going to write ijk twice. I take my first vector, which is u, and I write it 2, -1, 5, 2, -1, 5. I take my second vector v, write it twice, -6, 3, 8, -6, 3, 8. We need to figure out our first number. Our first number is the I. So you go up, and anywhere you find the I, you make a diagonal this way. That's your positive diagonal, just like your determinant. Notice, I could have made that diagonal there or here. You just have to do it once. It doesn't matter where you do it. You just have to do it once. Some of them you'll be able to do in 2 places, like I. Sometimes you will only have one option. So it's going to be -8, and then I need to be able to do I in the opposite direction. Here we go. And that one will be -15. Same numbers that I got in the other method. When I go to J, can you see that there's only one way I can make the diagonal go for J? And here I get -30 minus, and the only way that I can go J in this direction would be, oops, that's not red. Here, -16. And finally for K, here would be K, 6, minus, and the only way I can, I can have 2 options for going backwards on K, but I'll do that one. The nice thing about the arrow method is you don't have to remember that, I have to switch from positive, negative, positive with the determinant. So the determinant method, you have to remember this negative in the second step. With the arrow method, it automatically figures that out for you. And with the arrow method, then, what we're doing is we are choosing, in order to figure out what numbers go in the I part, that's why you write I, J, and K at the top. So you're like, if I'm connecting to the I, those are the numbers that are going in the top part, which represents the unit vector I. Then J would represent the second element, and K would represent the third element. Now we just found, that if we had these 2 vectors in 3 dimensions and attached them tail to tail, -23, -46, 0 is perpendicular to both of those and pointing outwards or inwards. And you don't have to worry about inwards or outwards because the actual numbers tell you that in that vector. That vector has a direction. It's already set. You don't have to where the heck is U? How do I put my right hand on it? Where am I holding my toothpaste? You don't have to worry about that at all in the Cartesian one because the answer already has its direction built into it. So the algebraic form is really nice because you do not need the angle. You just have to use the actual directions of the vector to get an answer. Now we could find the length of this, and we'd have the area of the parallelogram of those 2 vectors. consider these two vectors, and the cross product is W. So that means W is perpendicular to both U and perpendicular to V. Find the value of X. So what I'd like you to do is I would like you, on your own, to write down the cross product of U and V. I'm gonna and I guess it's not super clear in this question, but it would be U cross V because it was written U first and then V. Did you get your cross product? So now that we have that cross product, we know that 3x minus 4, well, that has to equal 2. And 3 minus 7x, that has to equal negative 11. And finally, that 28 minus 9, which is 19, has to equal 19. Absolutely. Now, from the first one, you could solve, right? From that first one, if 3x minus 4 has to equal 2, it's not hard to move the 4 over, divide by 3, and get that x equals 2. We should double check to make sure that that x equals 2 works for the second equation. If you plug in 2 for x, is 3 minus 14 negative 11? Yes. Okay? Did anybody use the other technique? Right? What do you like about the other technique? What I like about the other technique is you can kind of put your hand over it, like visualize it easier without having to write things out. So as a lazy mathematician, I tend to use, if I know technique number 1 well enough, I like to use it because I don't have to write as much. From a simplicity technique, this is less things to remember. You just have to draw the arrows and figure it out. So whichever one you did, you would have got the same answer. Now, we used the cross product to solve this. We didn't have to use the cross product to solve this. We could have used the dot product. And our knowledge of the dot product and cross product together. Okay? Our knowledge of the cross product says that the vector W is perpendicular to both U and perpendicular to V. The dot product tells us that if two things are perpendicular, the dot product is always 0. Because the dot product has cos of the angle, and cos of 90 degrees is 0. So we're going to do the same question. We would know that the dot product of V dot W has to equal 0. And the reason I'm using V and W is because V has the one with the X in it. So V was 3, 4X, dot product with W, and W was 2, -11, 19. That has to equal 0. Well, how do I do the dot product? I multiply corresponding one, 6, plus -44, plus 19x equals 0. In a lot of ways, this is even easier, right? But you will probably go the cross product route because the question says cross product in it. But if I solve for this, I'm going to get 19x, move the -38 over to the other side. I get x is equal to 2 that way as well. So we'll find in this unit with the cross product and the dot product or scalar product that it's really going to be thinking about what do they mean. Cross product is the answer is perpendicular. Dot product has cos theta in it. Cross product has sine theta. So we use them interchangeably. Here we have two vectors, and we want to find the area of the parallelogram formed between. So again, area of a parallelogram, that's related to cross product, whatever the length of your cross product would be. So I'll get you to find the cross product of those two, with whichever method you would like. And I'll write up the answer in a second. All right, did you get -7, 30, -33? So the area of the parallelogram will equal the length which is going to be the square root of -7 squared, 49, plus 30 squared, 900, plus -33 squared. I don't feel like doing that one. 1089. Square root of 2,038. Which gives us 45.1 units squared, whatever those vectors were measured in. Now that's the length of our cross product. To find the angle, we have options. We either have the option of using the cross product because it has sine theta in it, or we can use the dot product because it has cos theta in it. Okay? The problem with using the cross product is sine of theta is a positive number. Okay? You're going to solve for sine of theta, it's a positive number. It could be in quadrant 1 or quadrant 2. So you have no way of determining whether the angle was less than 90 degrees acute or bigger than 90 degrees obtuse. But if you use the dot product, your dot product will either be positive or negative, and you can tell whether it was supposed to be acute or it was supposed to be obtuse. So it is always better to use the dot product when finding the angle between two vectors. So how would I do that? Well, I'm going to find my dot product. Cos of theta is equal to the dot product divided by the length of u times the length of v. That was our formula from the dot product. So the dot product on the top would be negative 6 times 9, negative 54, plus 3 times 1, 3, plus a negative 4, or this is A and B, sorry. Look at that. I can't even tell that I ever wrote a U and a V. The length of A, 36 plus 16 plus 9. Square root of 61. The length of B will be 81 plus 1 plus 1. Square root of 83. So when we simplify this, we get a negative number. That negative number is telling us that the angle was obtuse, and you would have probably made a mistake if you went into the cross product. You probably would have written the acute angle just out of your habit of solving. So now I can do cos inverse of this answer, negative 55 over the square root 61 times 83. And I got 140.62 degrees. So what do we notice so far? What are the properties of the cross product? Changing the order does matter, but it just makes it in the opposite direction. So U cross V is equal to negative V cross E. you can distribute the cross product. I don't know why you would not want to add them up first, because that's a lot easier. But if you like to do more work, you could do the cross product with V and the cross product with W, and then add them up. Distribution can happen both sides. Okay? If the cross product is 0, that means that the two vectors are parallel. So we've got two ways of figuring out parallel now. Our first way of figuring out parallel is that you could just show that one is a multiple of the other one. When we solve for k, I like that way as sort of the best. But if you do the cross product and you get 0, which technically should have an arrow over top of it because it's a 0 vector, okay, then you know they're parallel. And the same is true if you go backwards. If they're parallel, the cross product is 0. Now, sometimes students see 4 and 5 and say, why did you write the same thing twice? Okay? We have to be careful. This is a logic thing. Just because something works in one direction doesn't work in the other direction. Okay? We could make a statement that all dogs have 4 legs. But the opposite isn't true. All things with 4 legs are not all dogs. Right? Oh, there's a dog. How do you know it has 4 legs? That sure looks like a cow to me. No, it's a dog. It has 4 legs. Right? So in mathematics, we always check, if it works in one direction, does it also work in the other direction? In this case, it does. Right? If the cross product's 0, then they're parallel. But if you started out with them parallel, you're going to find the cross product is 0. And if you multiply by some scalar, some number in front, you could either put that number in with the vector u or in with the vector v. It will not affect the cross product. Now, if you were taking a university class in this, they would probably ask you to show proofs of each of these. So what you would have to do is you would have to take some random u1, u1, u2, u3, v1, v2, v3, actually do the cross product, put k in there, and show that it didn't matter if you did this first or that first. It works out every single time to have this as a proof. If we did the cross product on this one, you get this one, -2 plus 4, you get 0. Do the same thing with the next one, you get 0. Do the same thing with the third one, you get 0. I guess second one you'd have -0 for a while, and then that would still be 0. And if you get the 0 vector, they're parallel. Just to remind you of the other technique, is there a k value? Oh, I'd probably put the k here. Put the k on either side, but this way the math is easier. Is there a k value that makes that work? Yes. -2 would work. Therefore, they're parallel. So these are 2 now methods of showing something's parallel. And now we have 2 methods to show that something's perpendicular. Perpendicular, we can either show with the cross product, because that makes sure that they're perpendicular, or we can use the fact that the dot product is equal to 0. And the last thing we're going to look at today is another application of the cross product, which is in physics, which is torque. And all torque is the cross product. So you might have learned a torque formula if you took physics, but now you can use an application of this where you have one vector A, which is whatever length of the arm. So if you have a wrench that's 10 centimeters long, that is your vector A. Your vector F is your force vector that you're applying, and you would apply that force at a certain angle. Usually, if you're smart, when you're applying torque, you push at a 90-degree angle to what you're trying to get to turn. If you ever, I don't think I've ever seen this, but have someone trying to push directly onto the nut with the wrench, nothing would happen. They push really hard, it's not going to turn, right? And since the length of your wrench is measured in some sort of units, like meters, and your force is measured in newtons, and this would become meters times newtons in the formula, it makes sense that your unit for torque is Newton meters. So again, a lot of these things get explained by just using vectors to represent. So we'll do, I think I've just got one question for you. Yeah. So we've got a wrench, 15 centimeters long. Oh, we will draw a beautiful picture here. There is a hole. We're going to have a blue wrench on here. Oh, yeah. Perfect. If this is 15 centimeters long, and you want a force of 50 newtons in a clockwise direction, so I am pushing on this here with 50 newtons at an angle of 85 degrees. Now vectors are free, so we have one vector here. This is vector u. This is our 15, length of 15. We can take the green one because the cross product is based on tail to tail. We can take it and move it centimeters, so if I'm measuring in meters, would you agree that that would be 0.15 meters? I mean, you could have torque in centimeter newtons if you wanted. That would be fine, but we often talk about it in newton meters. And if this gets translated over here, this angle and this angle, properties of angles will mean that this angle will also be 85 degrees.
Mr. Chair, why did you switch its hands on the other side?
Why did I switch the green arrow down here?
Yeah.
Because when we draw our two vectors for the cross product, they have to be tail to tail with the arrowheads pointing out.
Okay.
Now vectors are free.
Right.
This is, so you're pushing on it this way. You can say, well, that's like moving it down over
Yeah.
here. It's the same vector, but now I've set it up for my cross product. Okay? Which way is it turning? We're going this way after we push, right? That's the way the wrench would turn. So when you're doing your formula, it makes sense that if this is U and this is V, well, this is actually my length, and this is actually my force. I'm doing U cross V, and in the formula, it is A and F. So our torque vector will equal the length of A, which is 0.15, the length of our force, which was 50, times sine of the angle in between, times a unit vector, multiply this out on our calculator. 0.15 times 50 times sine of 85. What? Well, I'm in radians. It's like, this isn't working for me. I'm not liking the numbers. There we go, 7.47. That is better. We have to explain. Which way is the vector n going? Inwards or outwards? In towards the paper or out? Think about you can do the right hand rule, or you can think about turning something. Would that tighten your toothpaste or loosen it? It would tighten. So tighten would make the cap go in the direction inwards. You can do your right hand rule, but right? I find it's always hard to put your hand on the thing this way. You always want to put it this way, and then you're like, oh, my fingers don't bend backwards. What I find I don't like about the right hand rule is students will do this. They're like, oh, but if I bend just my pointy finger, well, then it's not the right. So the tighten and loosen seems to work better. And it also, I don't know, I like the intuitiveness that I'm turning it this way. The force is going in. Is that why we threaded things most likely that way? Does it have some sort of connection to pushing downwards? I'm not sure. But it sure is nice as an application. So, what's the magnitude? 7.47 Newton meters. What's the direction? Inwards. What angle is the best? Would be 90 degrees, because sine of 90 degrees is 1. Anything less than 90 degrees gives you something less than 1. And so you don't have as much power. That's why the person who's pushing directly on is like, it doesn't turn. Keep trying. Just keep trying until they start pushing the wrong way, right? And that will probably happen if you end up doing any kind of mechanical work or any kind of work where you're trying to take something apart and it has a bolt. There will be some times where you push the wrong way and you're like, it's not coming undone. And all you are doing it is tightening more and more and more. And you tighten it so much that you can't actually do it the other way. So you spend half an hour pushing one direction, tightening, pushing the other direction, loosening a little bit, but not thinking it worked enough, and back and forth, tighten, tighten, loosen, loosen, and it just stays there. So hopefully this can help you with that as well. Right? Ever learn the righty-tighty, lefty-loosey? Do you ever learn that? Here we go. Turn to the right, tightens. Turn to the left, loosens. Righty-tighty, lefty-loosey. This is really good English.